gonna just, we're gonna see, we gotta start talking about 4.1 right now. Oh, let's see, a couple other things about the test. True false you did really well on. Those were way too easy. But 8b, that linear transformation question, you know, it's only when the matrix is square, 8b on the test, when the transformation has domain Rn, codomain Rn, so when it's from Rn to Rn, that's when all those equivalencies of that invertible matrix theorem kick in. So only when you're going from Rn to Rn, same dimension, is 1-to-1 and onto equivalent. You know, if you're 1-to-1, you got to be onto. If you're onto, you have to be 1-to-1. I think back in chapter 1, I felt like we really kind of drilled it home that in general, when the dimension of the domain and codomain can be different, right, n by m, then you can be 1-to-1 without being onto or onto without being 1-to-1. But with that n by n situation, they're tied together. Like so many things are tied together when you're dealing with an n by n matrix. But that's all. If you have questions about particular things, just come and see me about it. And oh, I never want to grade a problem number 5 again. That was the most horrible thing. A lot of you were not describing your steps, so I'm staring at these matrices trying to figure out what the heck are you doing, and I think I figured them out. Sometimes, you know, you got to be careful when you try to do too much in your head at once, though. Some of you were in one step doing what was really 2 actions, and I think you didn't realize it was 2 actions. So if you have questions about that, if I wrote a note, just talk to me. I can understand why that's not obvious. All right, so let's start on our 4.1, and let's start talking about vector spaces. All right, we got the interesting stuff today. So this is the part of the course where we start talking about abstract vector space. An abstract vector space can be a set of just about anything. The things we call vectors, but they're not going to be vectors in the usual sense as column vectors with so many coordinates like elements of Rn or Rm or R3 or R4. Vectors could be functions. Vectors could be other kind of objects. The most common kind of abstract vector space you guys are going to see are function spaces, where the elements of the vector space are functions. We call them vectors, but they're not arrows. It just means there are certain properties that are satisfied, so all the theorems about vector spaces apply to these more abstract situations. We'll look at some examples. So what does it mean to be a vector space? Here are all the axioms. We're not going to dwell on these in detail because that's sort of a choice of our textbook, and I agree with it because it's hard to see the point of some of these properties that are so obvious. But basically, you have a set of objects where you have an addition defined. You can add them together. They might be functions that you're adding together. And the addition is, property 2 is commutative. That's the commutative law. Number 3 is the associative law. There's a 0. If you add 0, you're back to the same thing. There's an opposite of. If you add opposites, you're to 0. And in line 6, we're talking about scalar multiplication. So you can multiply the vectors by a scalar, whatever those vectors be. Trying to straighten that out. And then after number 6 are the properties that apply to scalar multiplications. Those are basically distributive rules. There's an associative law with scalar multiplication. And then it's actually got to be an axiom that 1 times a vector is always that same vector. When all 10 of those properties are satisfied, we say we have a vector space. And in this course, we talk about what are called real vector spaces. And in advanced math, the set of scalars is usually taken to be the set of complex numbers. It turns out there's a whole bunch of additional kind of properties and theorems and things that follow. So sometimes you talk about a complex vector space as opposed to a real vector space. The word real or complex refers to the set of scalars, whether it's the real numbers or complex. We're just going to talk about real vector spaces. So some examples. And so far, we've talked about Rn, meaning R1, R2, R3, etc. Those are all examples of abstract vector spaces. In a sense, they're the sort of concrete vector spaces that all our discussions have been based on. But example 2 now is something that might be a little bit new for you. We're going to use this notation, C followed by the interval 0 to 1. That notation stands for the set of all functions that are continuous on the interval in square brackets. So you could pick any interval at all. You could say continuous functions on AB. So it's just sort of an arbitrary choice to pick the interval from 0 to 1. The vectors in that space are functions. So a vector might be e to the x. A vector might be x squared. Might be one of my favorite functions is arctan x. Okay, those are all functions that are continuous on the interval from 0 to 1. It's not any old function, right? So just to kind of contrast things a little bit, I said note that the function ln of x is not an element of that vector space, right? Because you know very well that ln of x is not continuous at 0, right? It has that vertical asymptote at 0. So that's just so vector space. Well, a vector space means basically you can add the objects together. So you can certainly add functions together to get new functions, and you can multiply functions by real number scalars to get new functions. I mean, functions at first it seems kind of boring. But what this does is it opens up this whole theory of linear algebra to that situation, as we will see. All right, let's just keep going down our examples. Number 3 is going to be an example that we're going to fall back on a lot. So fix a positive integer, so 1, 2, 3, 4, fix that number. Let P sub n be the set of all polynomial functions of degree less than or equal to n. So that P sub n is a vector space. And let's just look at one special case. If n is 5, P sub 5 means all polynomial functions of degree less than or equal to 5. So you're familiar with what a polynomial function. Here's an example of a polynomial of degree 5. I just call it P sub 1 because now this subscript is different from that subscript. Sorry, this is a capital P. I should have made that stand out more. These are small p's. This just means the first function, second function, third function. I just didn't want to use the letter P over and over again for different functions, so don't mean for that to be confusing. So typical polynomial of degree 5, right, that first example. But the capital P sub 5 includes polynomials of degree less than 5. So x to the 4th plus 5, even linear functions, 5x plus 2. Why is that a vector space? You can add them together. You get another polynomial. You can multiply by a real number constant. You get another polynomial. That process works. So just think, to me, when you're learning about a new object in math, it's always good to ask yourself, do I understand situations where those properties are not satisfied or where I don't have a vector space? So just this note here, the set of all polynomials of degree equal to 5 is not a vector space. If you said they had to all be, so why Why not? Like, what's the problem there if you say polynomials of degree 5? So what's the difference between what I'm saying up here and what I'm saying here? Ed?
Well, you could add two functions of degree 5 and end up with a degree 4,
Yeah.
which wouldn't be.
Yeah, I mean that's exactly the point. So here's a degree 5 polynomial, let's say 2x to the 5th plus x minus 7. I could add to that another degree 5 polynomial, negative 2x to the 5th plus x cubed. And when I add those together, the x to the 5th term drops out, right? And I get x cubed plus x minus 7. That is not a degree 5 polynomial. So for the vector space rules to work, you got to be able to add two objects in your set and get an object that's still in the set. You can't fall outside of the set. That's where the fine print of the example P sub n, that's why we say the set of all polynomial functions of degree less than or equal to n. So this capital P sub n includes lower degree polynomials. So this is in P sub 5, this is in P sub 5, this is also in capital P sub 5. So that we just answered the why question there. Another example. Consider just two particular vectors in R4. So these are two column vectors. 1, 0. I just picked these out at random. 1, 0, 2, 0, 1, 1, 0, negative 1. Let H denote the set of all elements of R4 that have the form A times the first plus B times the second, where A and B are any real numbers. What do we call that? I don't know why I didn't use our official word for that. What is that? The length of those two vectors?
Linear combination.
All linear combinations of those two vectors, right? And then we also use that word. Have we used the word span already? So that's the same thing as the span of 1, 0, 2, 0. We used the word span already, right? Right. And 1, 1, 0, negative 1. I don't know why I didn't on the handout just say the span of those two. That's the same thing. Suspense builds. I guess we have to turn the page. So that set is also a vector space. In fact, we say, in this case, we say the set we got H, so my H is this guy. I'm still talking about that example from the previous page, is a subspace of R4. So when you have one vector space sitting inside another vector space, we call it a subspace. Is it obvious why that's a vector space? I think, I'm trying to think if we verify that in an exercise. If you take two elements in the span of these two, you're still going to have an element in the span of those two. If you take a scalar multiple times an element in the span of these two, you still have an element in the span of those two. So there's no way by adding or by multiplying by a scalar that you can end up with an element that is not in the span of those vectors. That's why it's an actual vector space. Is there a question? No. Yeah. So you got, most of you have this already. Last time, but if you don't, let me know. And now number 5 is really a super important example. Let B be the set of all real valued functions that satisfy, that's called a differential equation right there. Thank you. Okay. And you're familiar with this notation, right? We're saying the second derivative of the function plus 2 times the first derivative minus 3 times the function is 0. So there are actually many different functions that satisfy that differential equation. There are many functions that do not satisfy that.
Yeah,
show that B is a vector space. I guess I gotta, I think I meant to do that. So just, what we're gonna, I meant to do that, yeah. So I think we're gonna come back to this in a second. Because I don't want to do problems where we go through every single one of those 10 properties. Just realize I said that right at that point. So if we'll come back to this if it doesn't. I thought it comes up later in the handout, and if it doesn't, we'll come back to it. The theorem there is not terribly exciting. The following statements are true for any vector space. Zero vectors unique. 0 times anything is 0. Scalar times 0 is always 0. The opposite of a vector is unique, and -1 times a vector is equal to the opposite of a vector. But now, this is something we're going to focus on, and that's why I put it in a box. We are going to often verify whether we have a subspace of a particular vector space. So first let's just read through this definition. A subspace of a vector space V is a non-empty subset H of V that has the following 3 properties. All right. Number 1, 0 is in the subspace. You've got to have the 0 vector. If U and V are in H, then U plus V is also in H. And if U is in H and C is a scalar, then that scalar times U is also in H. So V is a vector space, H is some subset. We're wondering, is that subset a vector space in its own right? And it will be if these 3 properties are satisfied. So up here in the cloud, you can read that statement. Now we're going to start doing some problems here. So what I want to do is go back to that example 4. Example 4 was the span of these 2 vectors. I want you to verify that H is a subspace of R4. Right? That's the point of this exercise down at the bottom, where H is the span of those 2 4-component vectors. So first question is the 0 vector, meaning 0, 0, 0, 0 in H the answer is yes, right? The 0 vector is equal to 0 times 1, 0, 2, 0 plus 0 times 1, 1, 0, -1. So 0 is in the span of those 2 vectors. Right? We could even make a theorem out of this. If we wanted to, we could say the 0 vector is contained in the span of any set of vectors, because no matter what the set is, you can always take 0 times each one, add them up, and you have 0. So 0 is always an element of any span. So that was a very fine property. I guess let's call this A, not 1. Sorry, we're verifying property A. Property B, let U and V be in H. We got to show that U plus V is in H. So we need some way of writing this down. We need to introduce a little bit of notation. to, what I want to say is U's got to be a scalar times 1, 0, 2, 0 plus a scalar times the other vector 1, 1, 0, negative 1, right? And I need to denote these scalars in some way. There's no law about how to do that. I could say A and B. I could use, any letters I want. I might say U1 and U2. Or U1 and U2 are in R, right? Because that connects the scalars to the vector U, and it allows me to do a similar thing with V. So V is also a linear combination of those two vectors. So I just want you to see this idea that I'm just choosing to use U1, U2, V1, V2. But if you chose A, B, C, D, it's fine. They're just standing for real numbers. Observe that U plus V, which is going to equal this stuff plus this stuff, can be written as U1 1 0 2 0 plus U2 1 1 0 negative 1 plus V1 1 0 2 0 plus V2 times 1 1 0 negative 1. We know we've worked with vectors enough that we can write this as U1 plus V1 times 1 0 2 0 plus U2 plus V2 1 1 0 negative 1, which is in H. So we verified it's almost like span is just set up for being a subspace, right? If you add two vectors in a span, you get a vector in a span, because we end up with a scalar multiple times the first plus a scalar multiple of the second thing. And verifying property C is going to be real similar. Let's just write it out. Let U be as our B, just so I don't have to write it out again. Let C be a scalar. R, just a real number. And CU is equal to C times, now here we go, U1 times 1 0 2 0 plus U2 times 1 1 0 negative 1, which can be written as CU1 times 1 0 2 0 plus CU2 times 1 1 0 negative 1. And we're just, again, making the observation that this CU vector is a scalar times the first plus a scalar times the second, which is an element of H. So therefore, the three properties are satisfied. Subspace of R4. So we do have to know how to do that, how to work through those, the verification of those 3 points. It's kind of tedious to write out. Yeah. I know. I mean, you're overthinking. You're overthinking. We just want, U is a linear combination of these two. V is a linear combination of these two. We're just observing that U plus V can also be thought of as a linear combination of those two. And nothing more to it. All right, let's turn the page. Sorry, I did not give you much room on the handout for that. So some examples of subspaces. Geometrically thinking, any plane or a line that contains the origin of R3 is a subspace of R3. We've actually already talked about it a little bit in chapter 1. You've got to include the origin, because any subspace has to include the 0 vector. So a plane like the Z equals 1 plane in space is not a subspace. And that was sort of issue with that, those problems where we use homogeneous coordinates, where we had to go to a higher dimension to be able to work with it. Here's that C of the interval 0, 1 be this vector space of all continuous functions defined on 0, 1. Let H equal the functions in C of 0, 1 whose definite integral from 0 to 1 is equal to 0. Well, there are a lot of continuous functions defined on the interval from 0 to 1. But when we say the function is such that the integral from 0 to 1 is 0, that definitely limits us to a smaller number of functions, right? And there are some where that's true. That's certainly going to happen for some functions. It just means the area above the x-axis and the area below the x-axis from 0 to 1 cancel out, right? Like I can draw, imagine a picture 0 to 1. Say I had a graph where this is -1, this is 1. Even a straight line like that, the integral from 0 to 1, you're going to have some negative area here, positive area here. The integral from 0 to 1 is going to be 0. So whatever the equation of that straight line is, that's a function in that subspace. And I think we're going to verify that in a moment, so I'm going to just leave it at that as just an observation here. Also, number 3, every vector space is technically a subspace of itself. So we just got to get used to that. It just is a convenience when you're talking about subspaces to include the space itself. And the set containing of only the 0 vector is a vector subspace. So why anybody would care, I don't think many people do, but it's technically absolutely true that the set of 0 is a subspace. And example 5, P3, this is this set of all polynomials of degree less than or equal to 3, can be thought of as a subspace of P4, which is a subspace of P5, which is a subspace of P6. And we're going to keep coming back to these P sub n's. So just in general, Pn is a subspace of Pn if n is less than or equal to n. So let's do exercise. I think I'm gonna. So our exercise is to verify that this set of vectors, so these are a set of vectors in our three component vectors, such that x minus y plus 2z equals 0 is a subspace of R3. You know what that is? It's really just all the points that satisfy this equation. Because really our x, y, z column vector is just a point in space. And all the points that satisfy this linear equation in x, y, and z, you guys know, is a plane. And it's a special kind of plane because 0, 0, 0 satisfies that equation, right? So we're just actually going to go through the properties and verify formally that this plane in R3 that contains the origin really is a subspace of R3. And so we got to check the three properties. Check the three properties. Technically, property A is always implied if property B and C are already true. So in a formal treatment of this, people just verify property B and C. The reason we include property A is it's often easy to see that property A is not satisfied. And so as soon as you find out that property A is not satisfied, you know you don't have a subspace. You don't waste your time doing a lot of work when it's obvious you don't have a subspace. So, that we don't have to know that fact. We're just going to always verify all three properties. So A, the question is 0 H, and the answer is yes. Since 0 minus 0 plus 2 times 0 equals 0. So this is an x coordinate, this is a y, this is a z. 0, 0, 0 is h. 0, 0, 0 satisfies that equation. So if I had a different constant on the end here, like other than 0, if I had a 1 or a 2, that equation would still be a plane, but it would be a plane that does not include 0, 0, 0. And it would be a plane that is not a subspace. So only planes that include the origin are subspaces. B, we have to suppose we need our u and v. And because of the way I could write u1, u2, u3, because this is labeled x, y, and z, I might say u is x1, y1, z1, and v, which is x2, y2, z2. This would just be another way to approach it, are both in H. We have to show that u plus v is also in H. So, well, we know that the coordinates of u and v both satisfy that equation. So x1 minus y1 plus 2z1 equals 0, and x2 minus y2 plus 2z2 equals 0. U plus v, by the way, is going to be x1 plus x2, y1 plus y2, z1 plus z2. It's coordinate form. Okay. So I can just add the left-hand sides and the right-hand sides of this equation. going to regroup to make these sums appear. It's already here when I add those two sides together, or the two left-hand sides, and say they're equal to 0, but let's regroup to show everybody that we have x1 plus x2. We have, I'm going to factor out a minus sign, minus y1 plus y2, right? Factor out a 2 plus 2, z1 plus z2 equals 0. This means that u plus v is h. So b is done. C, let u be our x1, y1, z1 again, and let c be a scalar. So it's given that u is in h, so x1 again, minus y1 plus 2z1 equals 0. I want to show that c times u is an h, right? So you see we're going to just multiply both sides of this equation by c. And it's cx1 minus cy1 plus 2, I'm going to write it as cz1 equals 0. Right? Because cu is also h. And we have verified the three properties. So H is a subspace. Sometimes this gets a little more interesting. Verify that H in example 2, so H in example 2 is functions f of x in C of 0, 1 such that the integral from 0 to 1 of f of x is 0. We're going to verify that this is a subspace. What's 0? Consider f of x, which is equal to 0 for all x. The 0 function. That's just a function whose graph is the x-axis, right? So it exists. Or if you wanted, it's like y equals mx plus b, y equals 0 times x plus 0. It's like a line with slope 0, y-intercept 0. That's 0 over. The integral from 0 to 1 of f of x dx is the integral from 0 to 1 is 0 dx, which is 0. Thus, f of x equals 0 is in h. So the integral from 0 to 1 of the 0 function really is 0. The sub instead of u and v, because the elements here are functions, right? Wouldn't be wrong if you said u and v, but you could say f1 and f2, or g1 and g2. Yeah, there's no law about the notation that you use. Let's verify that f plus g is an h. So let's look at the integral from 0 to 1 of f plus g of x dx. The sum of two functions is just this. And one of the most famous and obvious properties of integration that you guys don't even think about anymore is that the integral from 0 to 1 of the sum is the integral from 0 to 1 of the first plus the integral from 0 to 1 of the second, right? And that's just 0 plus 0 because f and g are in the subspace, so the integral from 0 to 1 of the sum also has to be 0. Therefore, f plus g is an h. It's almost like you could just say it in words, right? Since the integral of the sum is the sum of the integrals, and the individual integrals are both 0, so the integral of the sum is 0. And let's verify the third property. C. So let f be in H, let C be a scalar. Let's look at the integral from 0 to 1 of Cf of x dx. So we're applying that integral to the function c times f. And another famous property of integrals that you take for granted, you learned it one of your first days in calculus, that you can pull a scalar out from the integrals. And so since f is an h, its integral is 0, c times 0 is 0, therefore cf is also an h. I mean, subspaces tend to almost satisfy these properties in an obvious way. And so H is a subspace of C01. So that one, we're running short on time. That one differential equation example I'll come back to next time. I didn't mean to just toss that off and not say anything about it, but I do want to get through the next couple examples, which won't take long, a few minutes. Theorem 1 on the next page. Right? We've kind of already said this, and so it's just sort of reiterating the fact that if V1 through Vp is a set of vectors in a vector space, the span is a subspace. The span of any finite set of vectors is going to be a subspace. And I go through properties A, B, and C in detail on the handout. We're not going to go through that together. And just down at the bottom, we say that a set of vectors V1 through Vp spans a subspace H if the span is equal to H. So this is just a little bit of vocabulary now. We're playing around with that word span. Sometimes we start out with the subspace, and we find out afterwards that it's a span of some vectors, right? It doesn't start out as a span, but we find out that there's actually a set of vectors that span it. So let's turn to the last page. There's a couple exercises here. We'll just get started on these. So on the last page, the exercise is let H be the set of all vectors in R3 of the form like this. 2A plus 3b, a minus 2b, where a and b are any real numbers. So I don't know what this thing is. This thing could be, we're not working from a single equation here, right? We're saying a and b are any real numbers. Show that h is the span of the set of two vectors. Well, we know that we can think of this as 2a plus 3b, 1a plus 0b, 0a minus 2b. We've done this type of thing over and over. And that allows me to rewrite this single vector as a times 2, 1, 0 plus b times 3, 0, negative 2. That's it. So h is equal to the span of 2, 1, 0, 3, 0, negative 2. So if you just look at that the right way, we can see that as a span. And b, h is a subspace by theorem 1. Any span is a subspace. So if you don't remember the number of the theorem, you don't need to know the number. You can just say, we know that any span must be a subspace. All right, I'm out of time, but I just want to, last example, and we're going to have to come back and finish this next time because I didn't get through it all. But I just want to compare that last example, the a plus b, a minus b, 1. So it says h is the set of all vectors of this type, where a and b are any real numbers. So they look kind of similar, right? Similar kind of exercise. So are these vectors the span of a set of vectors, or is h not a subspace? H is not a subspace. And there's an easy reason why. H is not a subspace because any vector in H has third component. It's like hitting us over the head. Equal to 1. It has to have a 1 in the third component. What does this mean? 0, 0, 0 is not in H. That kills it. That's why H is not a subspace. So that's where, if you can just see there's no way to get the 0 vector in there, it's not a subspace. So don't spend a lot of work trying to show it is, right? Like on a test, you want to just say, oh, no way, that one's not a subspace. I'm not going to try to show. So we got some things to come back to on Friday, and we will. And sorry to go over. And I got the tests. Other people were taking a little late. So